Hey there, in this video we're going to talk about the inverses of a matrix. So the first thing that I want to do is introduce you to the identity matrix. So the identity matrix has this format where you have 1 along the main diagonals. This is a 3 by 3 matrix, so usually we call this I sub 3 for the 3 by 3 identity matrix. So I sub 2 then will be the 2 by 2 identity matrix. It will be 1, 0, 0, 1. And so on. I sub 4 will be a 4 by 4 matrix with ones along the main diagonal. And so an n by n matrix, identity matrix, will have n rows and n columns and ones all along the main diagonal. So these are identity matrices. So what is the property of an identity? So the identity matrix has the property so that if you have a matrix A times the identity matrix, you get A back. So that's what the identity does. So think about when we add real numbers. So with addition or subtraction of real numbers, what's the identity there? The identity is 0. Is the number 0? Right? If I have like 5 plus 0, I get 5. So the identity is the element that allows you to do the operation, whether it's multiplication or in this case addition, that if I add the identity to a number, I get the number back. Okay, so if I have negative 3 plus 0, I'll get negative 3. For multiplication of real numbers, the identity is 1. So we say the multiplicative identity is 1 in the real numbers. And so using the same numbers above, then I will say 5 times 1 is 5. So 1 is the identity. And pi, that's a real number, right? Pi times 1 will be pi. So 1 is the identity. So an identity matrix is essentially the matrix that you multiply by any matrix and get that matrix back, which then means that you have to conform to our multiplication rules for matrices. So let's try an example. If I have the matrix, say 1, 0, 5, 2, and 1, 1/2. So what are the dimensions of this matrix? This is a rows by columns. So this is a 2 by 3 matrix. So the identity then needs to be the number of columns of the original matrix has to match the next matrix. So then that means I need to have a 3 rows for the next matrix. So that means that I'm going to use I3. So if I do this matrix times the 3 by 3 identity matrix, I'm going to get this matrix back. So let's try it. So what this says is if I have this matrix and multiply it by the identity 3 by 3 matrix, I'm going to get the original matrix. So let's see. So 1 times 1 is going to be 1 plus 0 plus 0. So I just get 1. And then I go to the second. So first row, first column, we get 1. Now first row, second column will give me the second entry here. So 1 times 0 is 0, 5 times 1 is 5, and then 1 times 0 is 0. So I'll just get 5. And now first row still, but now third column for my third entry there. So 1 times 0 is 0, 5 times 0 is 0, and 1 times 1 is 1. So notice that I got 1, 5, 1 again. And I do the same thing for these. So 0 times 1 is 0, 2 times 0, and 1/2 times 0. So I'm only going to get 0 here. Everything was 0. And then second row, second column, so 0 times 0 plus 2 times 1 is 2 plus 1/2 times 0. So I just get 2. And second row, third column. So 0 times 0, 2 times 0, and 1/2 times 1. So I'll just get 1/2. And so we get the original matrix. And so that's how the identity works. So how does that help us with inverses? And for inverses, so for a matrix, so we have to have our square matrix. So for a square matrix, so a square matrix means that the number of rows and the number of columns are the same. For a square matrix A, and let's say n by n, A inverse, so the inverse of the matrix is A inverse with the property that when you multiply A and an A inverse, you get the identity matrix. Right, so if A is an n by n matrix, then A inverse is also an n by n matrix. So you're going to get the n by n identity matrix. Only square matrices have inverses because the identity is a square matrix. So that's how you end up with that. So how do we find the inverse of a matrix? So let's do an example of finding the inverse. So I'll start with an example of a 2 by 2 matrix, and then we'll move on to a 3 by 3. So let's let the matrix A be 3, 7, and 4, 9. I'm going to do it the long way first. There is a shortcut, but I'm going to do it the long way so that then later we can appreciate the shortcut. So what we're going to do is we're going to create a new matrix. So we'll create the matrix A and its identity matrix on the other side. And then we're going to reduce A. We're going to try to put A in reduced row echelon form. So we're going to do Gaussian-Jordan elimination to get the left side that will contain A in reduced row echelon form. And so once we have that, so essentially what we're doing, once we put in reduced row echelon form, we're going to have the identity here, because that's what reduced row echelon form is. You have ones along the diagonal and zeros everywhere else, and you're going to have A inverse on the other side. So we're going to perform Gaussian-Jordan elimination on A, and as we perform the operations on the entire matrix, the identity over here on the right is going to turn into the inverse. So let's try. So we're going to create the matrix AI. So it's like an augmented matrix. So I'm going to have 3, 7, 4, 9, and the identity matrix. And so for Gaussian-Jordan elimination, we're going to label the rows. So I have row 1 and row 2. So our goal is to turn this into the identity matrix. So I want to make that 3 a 1. So how do I do that? So we're going to essentially divide row 1 by 3, or you can think of multiplying it by 1/3. So 1/3 times row 1 will yield the new row 1. So when I divide everything by 3, I'm going to have 1 4/3, and then 1/3, 0. And so that's what I mean by when we do the operations on the rows, we're going to end up with the inverse on the right and the identity matrix on the left. And let's leave the second one unchanged. So I have 7, 9, 0, 1. So now that I have a 1 there, the next step in Gauss-Jordan elimination is get a 0 underneath that 1. So that means we're going to multiply row 1 by -7 and add it to row 2 to get our new row 2. So that means row 1 stays the same. But my new row 2 comes from doing -7 R1 plus R2. Gives me the new row 2. So -7 times 1 is -7 plus 7 is 0. -7 times 4/3, so that's -28/3 plus 9. So let me do the math here on the side. So -28/3 plus 9. So that's -28/3 plus 27/9. So it gives me -1/3. And then -7 times 1/3. So that's -7/3 plus 0. So I'm going to have -7/3. And -7 times 0 is 0 plus 1 stays 1. All right, so I have 1 and a 0. So let's move on. So the first row is going to stay the same. Now we want to turn the second entry, the second column here, second row, second column, into a positive 1. So right now I have a -1/3. So we want to turn that into a positive 1. So let's multiply it by -3. So my new row 2 is going to be -3 times row 2 gives me the new row 2. So -3 times 0 is 0. -3 times a -1/3 gives me a positive 1, which is what we want. And then -3 times a -7/3, the thirds cancel and the negatives become positive, so I just get 7. And -3 times 1 is -3. All right, so I have 1, 0, and I have my 1 there. So now we need to get a 0 above that 1. And then we'll have the identity matrix there. So how do we do that? We're going to have to manipulate the second row. So now my second row is going to stay the same. So 0, 1, 7, minus 3. And now I need to get a 0 above this 1. So how do I do that? Well, I have a 1, so I just need the opposite of 4/3. So we're going to do -4/3 times row 2 plus row 1 will be the new row 1. So I'm multiplying this one by -4/3 and then adding it to the one above. So 0 times -4/3, that is still 0 with the 1. So I can just put, anytime I have a 0 and 1, I can just put the entry above it. Now -4/3 times 1 is -4/3 plus 4/3 is 0, which is what I wanted. Now -4/3 times 7, so that's our -28/3 again. So -28/3 plus 1/3 is -27/3, which is -9. And then -4/3 times a -3, the negatives cancel and the 3's also cancel, so I'll just get 4. Plus 0 is just 4. And so notice that I was able to achieve the identity on one side, and this is the inverse. So therefore we can say the inverse of the matrix A is the matrix -9, 7, 4, -3. And how can you check it? To check, we do A times A inverse. We multiply them, and I should get the identity. So my A, the matrix A, remember, was 3, 7, 4, 9, and matrix, that's a 4. And matrix B, or matrix A inverse, sorry, is the one up here. So it's -9, 4, 7, -3. And you might say like, they look kind of similar. Well, yeah, and that's essentially the shortcut. So, but let's check it. So I multiply first row by first column. So 3 times -9, that's -27. And my 4 was looking a little funky. So 3 times negative 9 is negative 27 plus 4 times 7, which is 28. So negative 27 plus 28 is 1. So that's in the first entry. Now I should get 0 because I'm trying to get the identity matrix. So let's see. First row, second column. So 3 times 4 is positive 12. 4 times negative 3 is negative 12. So 12 minus 12 gives us 0. And now here, this is now the second row. So second row, first column, I'm going to do second row, first column here. So 7 times negative 9 and plus 9 times 7. So those are going to cancel. Negative 63 plus 63 is 0. And now 7 times 4 is positive 28. And 9 times minus 3 is negative 27. So 28 minus 27 is 1. And so we get the 2 by 2 identity matrix. So they are in fact inverses. So that's how you check if two matrices are inverses of one another. And the shortcut for a 2 by 2 matrix is that if you have a matrix A that is A, B, C, D, then the inverse is the quantity 1 over AD minus BC. So A times D minus B times C. So you multiply the diagonals, kind of like a cross, make an X, A times D minus B times C, times you switch places of the entries. So the A and the D switch places. So I'm going to have D and A over here. And B and C stay where they are, but they become opposites. So minus B and minus C. So for our case, A was the matrix 3, 7, 4, 9. So let's try with the shortcut. So this means that A inverse will be 1 over AD minus BC. So 3 times 9, which is 27, minus 7 times 4, sorry, which is 28. So we get 1. And when I switch these, so I'm going to have A and D switch, right? So 3 and 9 are going to switch. So I'm going to have 9 and 3, and then the 7 and the 4 become opposites. So it'll be negative 7 and negative 4. And when you simplify this, 27 minus 28 is negative 1. So you're really multiplying negative 1 times this matrix. And so when you put in the negative, a constant outside of a matrix, you can just multiply each entry by that constant. So I get negative 9, 4, 7, and negative 3, which is what we got doing it the long way. So for a 2 by 2, this makes it a lot nicer, but unfortunately we don't have a shortcut. Well, we do have a shortcut for larger matrices, but that's not until later, a few more sections. So for a 3 by 3 matrix, we will do the same thing. So let's try an example of a 3 by 3. So let's let A equal 2, negative 1, 1, 4, 1, 4, and 1 minus 1, 0. So if I wanted to find a inverse, I'm going to do the same thing that we did for the 2 by 2. So I'm going to have 2 minus 1, 1, 4, 1, 4, 1, negative 1, 0. And we're going to augment it with the identity matrix for a 3 by 3. And we will proceed and do Gauss-Jordan elimination to get the identity over here. So 1, 0, 0, 1, 0, zeros, and then a 1. So that will be the process. And by the end, you'll have your inverse. So I'll do another video just to do this example.